on the second session of the day. And the topic will be for this session nano-enhanced and functional material in adaptive manufacturing. And our expert has been joined us, I think. Himanshu sir, are you listening me?
Yeah, you are audible to me.
Okay, thank you, sir. Our next expert is Dr. Himanshu Shishta. Dr. Himanshu Shishta is a postdoc research fellow in the Department of Metallurgy and Material Science at the University of Cambridge, United Kingdom. He completed his PhD and MTech in mechanical engineering with the specialization in advanced welding from the National Institute of Technology, Nagpur. He also holds a BTech in mechanical engineering from Gautam Buddha Technical University, Lucknow. Dr. Himanshu has previously held postdoc fellowship in the Department of Material and Metallurgy at IIT Delhi and at the University of Brigham, UK. He was awarded the MHRD Technical Assistantship for his PhD at NIT Nagpur. His expertise is focused on advanced welding and adaptive manufacturing processes. Dr. Himanshu has published a number of research papers in high impact SCI and Scopus indexed journals and has edited a book published by CRC. Over to you, sir, and thank you for joining us. Himanshu, sir.
Yeah, I'm just sharing my screen. Is my display visible to you?
Yes,
Hello.
sir. Yes, sir. Yes, sir.
Is it visible?
Yes, sir. It's visible. Thank you.
Perfect. Very good evening to everyone. Or technically, it's a good afternoon from my side. Just for a second, it's reading.
Good evening, sir. Good evening.
Yeah, perfect. So today I'm going to give a lecture on functional materials in additive manufacturing. A very thank you to Amritsar group of colleges and especially Dr. Gurbej Singh for making it possible. So I'm talking about the additive manufacturing of functional materials. There is always a criticism for the additive manufacturing, like about the scalability up to the industrial levels. Like with additive manufacturing, it's not, after investing millions and millions of pounds, it's not getting scalability. It's like very few commercial products are available. The way other techniques are doing pretty well, like casting and welding, they have been implemented in the industry since ages and such a large scale, while this additive manufacturing is lacking somewhere. So today I'm going to talk about the medical implants, which can be customized for the patient specific demands, and that can be scaled up to the actual products, and where we can utilize this additive manufacturing processes. So I believe all of you gone through the basics of the additive manufacturing, like types and everything. So I'm not going for much details in those things. I'm just discussing the additive manufacturing processes, which are usually used for the metallic materials. So for the metallic materials, we are using basically the powder bed fusion methods and the directed energy deposited. In the powder bed fusions, either we can use the selective laser melting or we can use the laser sintering as well, right? So instead of laser, if we are using the electron beam, then it's called the electron beam melting. So for the directed energy deposition, excuse me. So for the directed energy deposition, we are just supplying either the powder or a solid filler and side by side the energy. So we are not taking the gaps between the depositing of the layers. We are using simultaneously the energy and the filler. So that's how I'm going to discuss these two things, like the laser powder bed fusion and the directed energy deposition. So we are discussing about the advanced materials. So Today I'm going to discuss two advanced materials. The first one is nickel titanium shape memory alloys. That's I've selected these nickel titanium alloys because these are having a proven scalability and pretty good applications in the medical field and some of the structural applications. Our second material will be the one of the class of high entropy alloys. We called it medium entropy alloy, that we will discuss later in this session. So why this nickel titanium alloy is called a shape memory alloy? As the name suggests, shape memory. That means it memorizes its shape. I believe all of us have seen that wire experiment, like a wire has been banded, and if you're putting in a hot water or some lukewarm water, it's regaining its original shape. Why it's happening actually? So I'm going up to the atomic level, and from the crystallographic point of view, why it's regaining its shape. So this nickel titanium alloy, it has three phases usually. The phase which we are getting the wires and all these nickel titanium alloys, in the austenitic phase, that's B2 cubic, right? It's not proper cubic, it's called B2 cubic. So we call it ordered BCC. If we are deforming it, it's turning out to be B19, that's martensitic or monoclinic. There is one new interesting development is going on that we called as R phase. So I'm explaining through this diagram. So let's say that's B2 cubic and we are transitioning to B19 if we applied any stress or any external load. So that's a very conventional route, right? There is another great research are going on, like if we can found any alternate route where we have to minimum deform our material. In that way, we can enhance the life of the components, and that will be a great change, or it will be a great cost savior for the medical implants. So that's our modified route. Like we are going from B2 to R. Either we can return it or we can go to B19, and then that way we can return it. So these are the new routes that has been explored by the researcher, or a good amount of research is going on in these areas, and particularly our group is doing really great with these things. So what are the preferred conditions to form the R phase? As I'm saying, like this can be the modified route. So we have to know that, like how we can make this R phase stabilize at the room temperature in our material if we are deforming it. Sorry. So the first one is chemical composition. We can alter the chemical composition that will stabilize the R phase. We can introduce the precipitates. What these precipitates are doing, these precipitates are creating local stress fields, and that local stress field is helping the formation of R phase. We will see through the experiments in the later slide how it's helping the formation of R phase. And then the existing dislocations, that if you are from the pure mechanical background and you are unaware of about the dislocations, so in simple terms you can say like dislocations are the defect. These are the line defects in our material existed. If you are deforming any of the material, then the deformation has been stored in the form of dislocations or some other defects, let's say slip lines or some other defects. That's pure metallurgical term, so I'm not going into that. You can simply create an image like dislocations or line defects. So now these two things can be explored. Like we can say that like B2 to R phase transformation, that's competing with this conventional B2 to B19 transformations, and that's really remarkable. And why we are emphasizing this R phase? Because if we are applying, let's say 10% of the total strain, we can form the R phase and return to the original shape. So in this manner, we are not deforming our material too much. but this is limiting our loading application as well. So it's a trade-off between the application of the load and your recoverability or the life of the component. So that's very beautiful diagram. You can see it. If you're going to focus on this left diagram where my cursor is right now, if I'm making it laser pointer. So if I'm focusing on the left diagram only, so it's between the stress and the strain. And there is particular condition that has been highlighted close to this strain. Temperature is greater than the AF. I will explain what this AF is. As of now, you can say it austenite finish temperature. Earlier, I have showed you like what are the phases there, austenite, martensite, right? So when my temperature is greater than the austenite phase, means when my austenite phase has been stabilized at, let's say, some temperature, X temperature, and my temperature is higher than that X temperature, in that condition, if I'm applying any stress, if I'm saying my austenite phase has been stable, so the deformation has been started from the austenite phase. If I'm deforming it, I'm forming martensites, and when I'm unloading it, it will return to the original position. So that's called superelasticity. It's pretty low with the conventional, like say steels or some other materials, but with the nickel titanium, that's why we call it shape memory. We are deforming it up to a great extent, but it's returning to the original position because of this austenite to martensite transitions, right? Now, returning back means coming back to the second side, that's the right hand side diagram. If you will see this diagram, it's called stress versus strain. Now the condition is temperature is higher than the martensitic finish temperature. Don't worry about this austenite finish or martensite finish. I will show you in the later slide what are these temperature actually. So if my material is in the martensitic state initially, because I'm saying my temperature is greater than the martensitic finish temperature, that means my material will be in the martensitic state. Now I'm deforming it. It will form the D-twin martensite and it will return back. Now that's called shape memory effect, and that's called superelasticity. Now, if my material has been deformed and it's stored some deform, if I'm heating it, let's say I heated it, it will turn back to the austenite, right? If I'm cooling it, it will turn back to the martensite. So it's two-way deformation types. If I'm loading it, it's returning to the original position. If I'm cooling and heating it, then also the transformation is taking place. This figure has been taken from this reference. So look into that. Now, why we are focusing particularly on these nickel titanium alloys? Because, please excuse me for my cough. There is pretty cold outside, so I'm feeling it. Sorry for that. So why we are focusing on this nickel titanium shape memory alloys? Because it have very established industrial applications. First one is morphing of the aircraft wing. If any one of you are aware about the latest update with the aircrafts, at the Navy ships, they have the capacity to land the aircrafts. What they are doing when the aircraft is landing, they are tilting the wings of the aircraft so it can accommodate in a lower space. And when we are returning back, we are expanding the wings and it can go up to its full efficiency. So to minimize the space on these aircraft carriers, this function is pretty useful, where we are using the morphing functions of shape memory alloys. Second thing is robotic hands. In mechanical engineering, particularly this robotic stream, we are using too much of shape memory alloys, like how to control the hand movements and all these movement applications. We are using shape memory alloys. The next segment is medical devices. That medical sector have a huge scope for the patient specific customized implants, and that's where we are focusing to create a very cost effective and affordable mechanical means this biomedical implants. So we are rigorously focusing on these, and this have a great potential to take up to the industrial scale or make it commercially viable for all the patients who need any implants or anything. So I believe all of you have seen that the braces of, so if someone's teeth are not properly aligned, they're taking the medical aid kind of a braces on their teeth, and later in due course of time, the teeth are coming back to the properly aligned position. And why it's happening, let's say where my cursor is right now, you can see the braces of nickel titanium alloy. If you have applied a stress on this wire and then fixed to the human teeth, now what this wire will do, in our earlier slide, I told you, like, if you have applied some stress, it's going to the martensitic state, and now you remove the load and fixed it with the wire. What it will try to do, it will try to return back to its original position because the load has been removed. And in that way, it's correcting the teeth positions, and that's how it's working. The next segment for the biomedical implant is cardiovascular stents. Is anyone saying something? Hello. Is
Hello,
everything
sir.
okay? Is everything okay?
Yes, yeah, okay, sir. Please continue.
I thought I heard some sound, so I was like, is someone saying something?
Okay.
Okay. Thank you. So the second most important thing for the medical devices are cardiovascular stents, where we are focusing rigorously. At present, these cardiovascular stents are hundreds and thousands of bucks. We are trying to minimize it to make it just few thousands of bucks so anyone can afford a good patient-specific implant. So our main focus is on this. We will go in the later slides for a detailed investigation on these patient-specific cardiovascular stents made with the additive manufacturing method. Now, the another thing is you can see these uh, variable geometries for the chevrons for the Boeing aircraft. That's the latest update. They're doing it. Very few details are available because that's commercially protected, that they're patented product. The other application of these nickel titanium alloys is in protection of buildings in earthquake. That's we discussed recently, like these are super elastic, so it can sustain more with the earthquakes. And for the damping of the means these cable bridges, so that can also enhance the life of any of the cable bridges. Now that's our actual additively manufactured product which we printed in our lab. So that's a laser powder bed fusion printed cardiovascular stent. When any artery or any blockage is there in any human body, we are putting these cardiovascular stents. So what it, let's say I squeezed it and put it into the human vessel. What it will do, it will try to regain its original position. That means it will try to expand, right? That's what we want. We want to open that artery, so it will try to expand. That's how it works. So these are the printing parameters. So we operated a laser at 80 watt. That's for the scan and speed side and all these things. So the composition of this printed product is nickel is 50.9 atomic percent and titanium is 49.1. Right. So that's called roughly a near equiatomic nickel titanium alloy stent. And in the second image, the image B, you can see it. That's the scanning electron microscope SEM image, where you can see it, how the surface features are there. The another thing is this product has not been heat treated or anything, so that's why you are seeing it like this, no grain boundary or anything. In the inset, you are seeing a highly magnified image. So what are the objectives we are trying to achieve by printing these cardiovascular stents? So we are fabricating, let's say, it depends on human bodies, like how is their blood pressure and how is their body is reacting, what kind of strength a human need, you can customize based on particular human need. So that's why I'm saying you can make it really cheaper and affordable, as well as you are giving them a specific product built for them only. So that's a huge opportunity if anyone wish to tap it. And now the second thing which I wish to highlight for my talk is synchrotron diffraction. That's a capability a very few countries in the world have, and luckily we have one this synchrotron beamline facility in UK. The name of that synchrotron facility is Diamond Light Source. If someone would ask you what's the power that's flowing through your house, it's like, let's say 200 or 220 volt. If you are transmitting a power, you are transmitting at, let's say, kV, or you are using SCM or XRD, the lab scale XRDs, you're using the kV of the power. That means 3 times higher. If you are having really heavy or bulky equipment, I've not seen any equipment. I've worked with many advanced labs in India, but I have not seen any equipment that's going up to the 10 to the power 6 of powers in megawatt, you can say it, megavolt. Here, why I'm emphasizing particularly on this, because the synchrotron beam lines, they are using the power up to the giga scales, means 10 to the power 9. So we are using a 3 gigawatt of power source for generating the X-rays or the neutrons, whichever you want to analyze your material. So I'll show you specifically how it works. So before going to that, I'll show you other members from my group. They have optimized the designs, this zigzag and palmage designs. So we are going ahead with the zigzag design of the stent. So that's the synchronous beam line. That's the actual photo of a place. It's called Diamond. It's close to the Oxford, University of Oxford. The place is Oxfordshire or Didcot, you can say it. So what's happening here in figure 1, you can see it. There is some inner ring, and from that inner ring, different chambers are coming. So one chamber is equivalent to one beam line or one experimental facility. Similarly, second experiment can be, means the second group can work here, third group can work here, fourth can work here, and simultaneously different groups can work there. What they're doing, they're using really big electromagnets, and they're running high speed or close to the speed of light. The electrons are moving in it, and you are bending the electrons, right, with the help of electromagnets. And during the bending, electrons are releasing energy in X-rays. We are channelizing that X-rays in this region, in these experimental boxes, and there we are doing these diffraction experiments. I am emphasizing on it. Let's say you are using some lab scale XRD. You spend at least 2-3 hours to get a good diffraction pattern, right? I believe most of you are aware about the diffractions. So it usually takes 2 to 3 hours to generate a good diffraction patterns. Here in this facility, we can generate in fraction of seconds, even less than a second, you can generate a diffraction pattern. Now, can you imagine how much of data you are generating? Let's say you are doing some in situ loading experiments, right? You didn't know if what's happening. Let's say your material is in phase A, you deformed it to material, means you deformed it to in phase B. So what reactions happens between phase A to B, you don't know, because you are getting either a phase A or phase B, because the The recording time for a diffraction pattern is 2-3 hours for a lab scale XRD. Here, it will take fraction of seconds to generate a complete data set, right? So that's why these facilities are very limited in the world. One is in UK, one is in, for the whole Europe is in France, I believe, ESRF, European Synchrotron Facility. One is in Spain, I believe the name is ALBA, ALBA. So that's how they have these synchrotron facilities. In US, they have 3 or 4. Apart from this additive manufacturing thing, I would recommend all the researchers or whoever is listening this talk, this synchrotron beamline facility is free to use, right? For anyone, irrespective of their nationality. The only thing you have to do is write a proposal, like what you want to do, submit it to them. That means the project submission deadline is almost always open. In 3 months or 4 months of phases, they review the proposal, know whether they have accepted your proposals or not. Write a proposal to them, what you want to do. If they find it like worthy to go via the synchrotron, you will get a free time slot for it. Otherwise, if you are paying for it to use it, I would say it's roughly 5 lakhs per day in Indian currency if you want to use this facility. So I did a lot of experiments as a principal investigator or co-PI at this facility. If anyone wish to know anything about it, please let me know after the talk. So I showed you like these are the boxes where you are performing your experiment. So that's one beamline, that's second, that's third. So out of these beamlines, that's your experimental chamber where you are using actually the X-rays. So that's behind this, there are multiple chambers through that X-ray is coming. And here is your sample. So X-rays are passing through your samples and these are the collectors. The specialty of this dual imaging and diffraction beamline is that's only first in the world, and luckily we were the first group in the world to utilize this facility. What you can do with this facility is that's for the imaging purpose and that's for the diffraction purpose. So you can image your material and record the diffraction patterns as well. So you can see it, what's happening on your surface and what's happening inside your material simultaneously. So what's going on through here? You are receiving 2 X-ray beams instead of 1, right? So 2 X-ray beams are incidenting on your material, and simultaneously you can change the detector. That's a robotic arm. During the experiment, you cannot be inside this chamber because the X-rays are of very high power or high intensity. It can kill a human in minutes, right? So you cannot be inside this chamber. So a robotic arm is doing the interchange of detectors for you. So it's a pretty good and seamless switching between the diffraction and imaging. And 2 independent X-ray beams are coming. And one thing I will emphasize, why I'm showing these characterization facilities is like this additive manufacturing is always criticized because of this applications. Like we are not having too much of industrial scale applications of it. So before going to the industrial scales, you need to have really a good characterization. Then only you can claim your product is pretty good. Then only you can scale it up to the industry levels. So you have to go through this if you want to develop any product using the additive manufacturing. So that's why I'm taking you through all these things. So that was our experimental plan. So what we were doing, we were passing a synchrotron beam, the incident X-ray beam, through our stent. I've shown you one SEM image of a stent. So that's the same stent. That's just a schematic representation of the stent. So here the tomographic imaging camera, you can see it. And these are the diffraction rings you are getting. Actually, you can convert these diffraction rings into diffraction patterns you have seen in the labs. So you can integrate it and you can convert it later. So I'll show you the results, how it can be done. So what we are doing, we have taken 3 stages. The initial stage, where just the additively manufactured stent has been exposed through this synchrotron X-ray beams. Then we are squeezing it. That means we are loading it and seeing how much deformation is going through it. And the third section, we are unloading it, and then again we are exposing it to this X-ray beams and seeing how much deformation has been retained in the material, or was it 100% reversible, or it's turning to its original position, or some deformation or strains has been retained there. So to capture these things, we have taken the 180-degree rotation of the tomography. That means for this imaging thing, we another thing which I would highlight here, you can rotate your stage only where your sample is. You cannot rotate either the detector or X-ray beams, because the X-ray beams are at very high energy, so you cannot disturb them. So you can rotate your stage only. So you have rotated the stage by 180 degree to capture the tomography, and for the diffraction, 360-degree rotation was there. Before going to the detailed explanation of the diffraction data, we have performed some basic EBST. For the EBST, the edge printed stent has been taken into consideration. So a full scale complete EBST has been captured. So you can see it, how the stent one segment is there. Now we have captured the EBST. If you are not aware about the EBST is called electron backscatter diffraction. It's performed using the SEM machines, the scanning electron microscopes. You need specific detectors to collect the diffraction patterns coming out from the material. So I'm not going into too much details of it. So what we are capturing the EBST patterns up to 0.1. So there is no edge or curve in the stent. So the first point is showing us up to the 0.1. Second is where the stent is bending, we have captured the stent junction. So that's called inverse pole figure, APFZ. Second thing is grain orientation spread. And the third thing is kernel average misorientation, CAM maps. So in simple terms, we will see if higher CAM value is there, you can say it, more deformation is there. The similar is the case for GOS. You can see it for 1 to 2 degree, this blue color, it's pretty high here. Here, mostly 0 to 1 degree. So that means at the junction of the stent, there is too much deformation. And the thing is, we have not deformed it. It's during the additive manufacturing only. So you can say it, that was because of the dislocations only, or the line defects. So these were because of the line defects. So the dislocations, you can see it, much of the greener color in this figure compared to this. Now, DSC maps, differential scanning calorimetry. During my start of the talk, I told you about the austenitic finish temperature or martensitic finish. So that's the heating cycle, that's the cooling cycle, right? The black one is the cooling, this red one is the heating cycle. So if I'm heating my material, heating means it's not really heating, it's up to 25 degree only, right? So if I'm heating it, let's say here is the martensitic phase or the R phase, whatever you call it, because either you are finding R phase or martensitic phase if you're not deforming it extremely. So austenitic start temperature, that means austenite phase has been started forming here. And when you have reached to the austenitic finish temperature, that means after this temperature, the complete volume will be the austenitic structure, the B2 cubic structure. So that's you can say it. When the temperature was higher than AF, that means we were in this side, and the temperature was higher during this MF. That means we were on this side. So that's RS. R phase is start temperature. S is belongs to starts, and F belongs to finish. You can replace it with the Martin side, but here you can see it. The hysteresis is pretty low, so you can say it. That's R phase, not the Martin side. Here also. Now we have mapped the hardness as well, because you cannot claim any product without the mechanical properties. And this stent was pretty small, so you cannot measure the hardness or other mechanical properties using the conventional ways, right? So you need something special to measure it, and we have used a nano indenter, right? That's an optical image. Here the scanning electron image of the same region that you can see it. This edge you can validate it. That's there. And we have measured the nano indentation hardness in this area, and we have magnified it. Can you see a series of or array of stents is there? So we have mapped the hardness of this whole area by placing the indent at a proper distance, and in a series of hardness mapping, we have created a map. So here you can see this in diagonally of this junction, we are getting a pretty good amount of hardness. It's because when you have seen the EBSD map, you can see it in this region, particularly where the junction was there, high amount of dislocations was there. That means the defects were there, and higher defects are leading for the higher hardness. And the average of hardness was somewhere 8 gigapascals or something was there, and that's the well within the already documented hardness for the additively manufactured components. Now coming to the synchrotron analysis. So for the tomographic reconstructions, tomography means the imaging thing using the X-ray diffraction. So we have not completed the whole stent from top to bottom, right? You cannot cover it. It will take a long time in covering it. So after initial state and then the loading state, you can see the fraction of this nylon wire, and then in the unloading state. Now the representative X-ray diffraction patterns. In the earlier, I've shown you a few rings were there, white rings were there on the detector, and you can integrate those rings and make a diffraction pattern. And one more thing, if you are interested really in the research, I would like to highlight, all the researchers can note it down. When you are plotting any of the XRD graph, right? Plot it with respect to the intensity. And here we used to take usually the 2 theta. Don't plot it with 2 theta, plot it with D spacing. That means with the lattice parameters. So what you are avoiding it here, let's say I used a certain wavelength in my conventional lab-based XRD, 2 theta will be different. If I used a synchrotron diffraction source, my 2 theta will be different based on the wavelength, right? 2d sine theta into equal to n lambda. That's Bragg's law. Luckily, the person who invented this Bragg's law is just close to our lab. Means the person who invented this Bragg's law, he was from the Cambridge University, and there is a lab in the name of that fellow. So that's close to us. So if you are plotting it, plot it with the D spacing. This D spacing is not changing with respect to this applied energy or the wavelength. So keep a good practice of plotting the data. Now returning back to it. Edge received, that means we are saying it, just the edge printed stent was there, just a B2 cubic phase was there. When we have deformed it, several new peaks has been evolved, right? That peaks belongs to R phase. Each peak belongs to the Martin-Slick phase and some R phase again there. And when you unloaded it, this peak has gone. A small amount of Martensite has been retained there. So you can say it, the recovery was not complete. Completely perfect was not there. Some amount of martensite has been retained in the material even after you remove the complete load. This blue image, right? Now we did some analysis for the stent. That's the normalized intensity we have plotted for the R phase intensity B19 and B2 cubic. All three intensities has been plotted where the rotation was 360, right? This omega. Now we calculated the stress tensor. One thing I would like to highlight, that's for the omega omega, omega y and yy. So in this yy tensor or omega omega tensor, you can see it close to these edges, from one edge to another edge, the high stress regions were there. The high stress regions were there. All the high stress regions were approaching from one corner of the that stent gap or stent hole was there from the another. So it may be most probably because of the stress concentration is higher at this age. So most of the dislocations or defects are settling in these areas. Then we measured the von Mises component of the stress and the R value, that means the fit index, that's pretty bad when the edge fabricated. That indicates there was no B19 or R phase was there. When we have loaded it, the fit index has been improved significantly, right? At least 10 times. So this R value is going to 0.443. When we have unloaded it, again, R index is going down, means this R index is, fitting index is going pretty down. So we can say you cannot quantify it properly because the fit index is not that good. But when you compare with the edge fabricated and unloaded, you can claim it like during the loading condition, these phases are forming, and which we have captured during the XRD maps which I've showed. Based on these results, we published an article in Material Characterization. You can go and read in more details about these results. So there are few conclusions based on these results. When you are applying a cylindrical strain, let's say roughly 1%, the two phases has been popped up. So B19 and R phase has been popped up. And when you're applying the stresses, roughly 400 megapascals of the stress has been generated close to the stents. That's pretty huge amount, and that's most likely is a precursor to form the martensite in R phase. The nano indentation is also claiming the same thing because regions near to the stent junction, it's having pretty high hardness. The similar way, the EBSD characterization is also indicating the same thing. Do you remember the first slide which I showed you? Here we are claiming it like because of the cylindrical strain, two new phases have been formed, B19 and R phase, right? If I'll go to the first slide, just let me take you to the first slide. Do you remember it? That was a conventional route, B2 to B19. Just only one phase has been formed, single step transformation. And in a modified route, you're going from B2 to R, then you're going to B19. So you're going via lower stress way. So that means you are improving the life of the component. So that's what I want to highlight, like that's a modified route that has to be explored, and that cannot be explored with the conventional methods like normal XRD or SEM. You need high-end characterization tools. Then only you can claim your patents and commercialize your products. right? Now we have heard too much about the dislocations, like how the dislocations are increasing the hardness and all these things. So someone might have questions like, means how these dislocations are affecting. So to go through the additively manufactured these cardiovascular stents, it's a pretty difficult experiment because we have customized a lot of things for this. So what we do to make it simplify, we have taken a nickel titanium plate, and that plate was rolled in the initial state. So a lot of dislocations were there already. And we are heat treating it for 1 minute, 2 minutes, 3 minutes, 4 minutes. And that's the dwelling time, right? So what we did, first we waited for the furnace to reach the temperature of 850. After reaching the 850, now we are putting the sample, not from the initial, right? So that's just a dwell time of 1 minute. We put it for 1 minute, removed it, 2 minutes, removed it, 3 minutes, and 4 minutes. Right. Here is the IPF jet map. So you can see it. There is no heterogeneity in the material, right? The orientation is almost the same for all the specimens. All these 4 coupons or the samples are different. It's not like I took one sample, heated it for a minute, characterized it. Now heated it for the same sample for another additional 1 minute to make it 2, then characterize. It's not like that. We have taken 4 different coupons to see how it behaves. Now the CAM, kernel average misorientations. Excuse me for a second. Let me take a sip of water. Did I show you in my last slide, if you remember? You have seen these green things. That's what I claimed, like the higher deformation area or the higher dislocations area, right? But we have not calculated any dislocations or anything here, right? Now, with these experiments, we are doing that thing. So the higher green area is there as kernel average misorientation. If you are seeing what does the misorientation means, let's say you have one point and it have an orientation of, with respect to the reference plane, 0.4 degree or something, and the another plane, the another data point that is having a 0.6 degree of misorientation. In that way, you can with respect to the each successive point, you can calculate the average misorientation values. So you can see it. If you can see it here, few white lines are there. If I have to zoom it, believe you will be able to see. Can you see a lot of white patches are there, and these white patches are getting diminished with the increase in heating time, right? Few has been retained there for 1 minute, when you are going for 3 minutes, and then you're going for the 4 minutes, it has been almost eliminated, right? Why I zoomed it? That's called low angle grain boundaries. If you are aware about it, there are 2 types of grain boundaries, low angle and high angle grain boundaries. And that's a usual convention is most of the deformations or dislocations are settling down at the low angle grain boundaries, right? So here a lot of white lines are the in this analysis, we are showing white lines as low angle grain boundaries, and the proper black lines here also the same thing as the high angle grain boundaries. So in the adhesive condition, too many of white lines are there. So that means too much deformation was there, because to convert from a slab of NITI to a slab of NITI to a sheet, we have to roll it. So during the rolling, a lot of deformation has been accumulated here. You can see in the form of cam maps, a lot of green or even yellowish range we are reaching. Blue is the lowest one, and green or yellowish is on the higher side, right? You can see this scale on the 0 to 5. So we are in the yellow and green region, so we are on the higher side. When I heated it for a minute, it has been lower down, not that significantly, but at the 2 minutes, it's showing a drastic change, a significant recovery after 2 minutes of heat treatment, and then 3 minutes and the 4 minutes. So with the increase in time, or we have not showed the results here beyond the 4 minutes, because after the 4 minutes, it's almost recovered, means all the dislocations has been almost recovered. Now, in this experiment, we have calculated the dislocations. That's called GND, geometric necessary dislocations, right? So before going to that, one thing is grain orientation spread. The same thing is there. It's on the scale of 0 to 10. So you can say it 10 is on the higher side. So initially it's on the higher side. When we are heating it, it's going lower and lower, and you can say it, the material is getting stress-free with the heat treatment, right? It's recovering. For the geometric necessary dislocations, that's a scale from 10 to the power 12 to 10 to the power 16. You can see it with the heating. It's also following the same pattern, or even you can see it the way GOS was there, similar way it's there. This GND has been calculated using the MATLAB, and the remaining things has been calculated using some commercially available softwares. Now, a pretty good thing, the DSC measurement, the differential scanning calorimetry. So we have gone through in very detailed calculation for these heat treated specimens. What we are doing for the edge received, a black line is there. You can see it. Abrupt change is there around 25 degree, right? Where my cursor is. I believe you can see it. Let me make it to highlighted. So here you can see it. It's roughly 25 degree, right? When I'm heating it, let's say 1 minute, 2 minutes, 3 minutes, 4 minutes, this abrupt thing is going away, right? So we are saying it, this abrupt thing was there because of the dislocations, and when we are heating it, it's going away, right? However, area under the curve, that's what we call enthalpy of transformation. So we are cooling it, right? If you remember from my earlier slides, I told during the cooling, we are going either the martensitic or R phase, and that's austenitic phase. So here, the austenitic phase will be there, and now we are cooling it. It's transforming to martensite, right? The area under the curve is called the enthalpy change to form austenite to martensite, right? And when I'm heating it, area under the curve is increasing. Can you see it? Area under the curve is increasing, and there is a slight shift towards right. So area under the curve is called enthalpy change. So the enthalpy of transformation is increasing with the heating. So you can keep this line in your head. I'll show you how. Some grain size has been measured with the isothermal dwell time. Not too much change was there. Cam, I showed you in the map as well, and here is the numeric calculation. So for the 0 degree, that means the edge received plate, there was too much of cam value, kernel average misorientation, and when you are heating it, it's turning drastically, right? So grain size has not been changed too much. So we can claim it, whatever changes we are getting, it's because of the dislocations only, right? Not because of the grain size, because the fraction grain size is changing in the fractions, and it's changing significantly. You can say it like from 7.75 to, let's say, 7.5 or even less than that. So that's what the change is in the grain size. That's well within the error range. However, the kernel average misorientation or the dislocations are really coming down. Now we have plotted a graph between the enthalpy change and the GND density, right? Enthalpy change means area under the curve, right? So area under the curve, that means this black line, it's increasing. That means enthalpy of the transformation is increasing. Now we have to supply more and more energy to transform our material, right? However, this GND density is coming down. You remember the EBST thing, GND density, it's coming down, right? We are moving from green to the blue color with the increase in the heating time. So what does it mean? Like if we are at a zero load, we need a low amount of energy for the transformation. But why? Because there was high amount of dislocations was there, GND density was there, dislocation density was there. So what it means? That means dislocations were helping you in the transformation of austenite to martensite or vice versa. If you are lowering the dislocations, you need more and more energy to transform the materials. So now dislocations are helping you in two ways. First, it's not allowing too much of deformation. The second, it's helping you or assisting you in the transformations. That means you need a lower energy for the transformation. We did a lot of work with the orientation, dependency, and these things there. And these results have been published really beautifully and well appreciated by the academia. This has been recently published in 2025 in the Scripta Materialia. I would recommend if you are interested in the shape memory alloys or biomedical implants, please read this paper. This will help you in clearing a lot of your doubts. Now coming to the medium entropy alloy, that's a class of engineering alloys for the space applications. So it's close to 1 hour. Shall I? Okay. So that's the schematic illustrations. What we did in this segment of experiments. That was also a pretty beautiful series of experiment which we did as a IIT Delhi group. I was working in IIT Delhi at that time, and we had a collaboration with some Taiwanese universities. So it's research work from that time. So I hope you will enjoy it. That's a pretty good results we are getting. So what we did, we have printed using this raster scan strategy. What's this XYZ direction? So what we are believing, XZ and YZ, it will give us the same set of microstructure or mechanical properties, while this XY will give us a different set of properties because of it's the top layer, right? So this has not been heated multiple times. So it shall have pretty different microstructure than these ones. So we have taken into consideration the XZ and XY surfaces, right? So that's directed energy deposited, DED, right? Not any powder bed fusion or something. Then we did a hot isopress sintering, hot isopress static sintering, and then hot rolling process was there. So we first printed a sample, then we have passed it through two different stages. One set of samples we have collected here, then second set of samples we have collected there. Now we will try to compare what this hot isostatic pressing is doing and what this hot rolling is doing. So here is the good set of SEM images. That's for the XZ surface, and that's the XY surface, right? And in the inset, you can see the zoomed version of the places. So for the edge printed specimen, you can see a lot of porosities that has been highlighted in yellow color circles. You can see them, a lot of porosity was there. When you are applying hot isostatic pressure, what does this mean? The temperature was high when we are applying pressure from all sides. That's why it's called isostatic pressure and at the high temperature. What it did, the heat changes the crystallography, and as well as it minimizes the porosities as well, right? And when we are hot rolling it, it changes everything, right? During the hot rolling, new crystals are forming. You can see it, twins were there, and the porosity has been almost eliminated in this case. You cannot find the pores there the way it was available there and there. So we calculated the porosity measurement using the standard Archimedes principle and use the standard density and the measured density. And then you can calculate the porosity volume frictions, percentage of porosity, edge built, it's pretty high porosity in percentage. And when you're going for the hot isostatic pressing and hot rolling, it's almost close to the standard theoretical density. So very less porosity was there. Now we have captured the XRD spectrums. Now with the XRD spectrums, we are getting a pretty good idea. Let's say we are focusing on this first row. So that's XZ surface, that's XY. For the XZ surface, you're seeing the orientation is preferred in 111 and 200 directions. In the XY surface, it's preferred in 220 directions. So that's a clear-cut case of microstructural heterogeneities, right? When I applied hot isostatic pressing, still 220 is prevailing, while here 111 and 200. When I applied the hot rolling, it's beautiful. The heterogeneity has gone. All the peaks are almost similar, 111, 20, and 220. Now, to visualize it in more effective manner, we performed some EBHD measurements. So here you can see it, as the edge printed, XZ surface and XY surface. And you see the heterogeneity. That's a green color, a different orientation. Here you can see it. Different orientation, this triangle is showing you. So here the orientation is different, here it's different in case of edge printed. Another thing which I would like to highlight for you, a lot of dislocations are there. White lines has been identified as low angle grain boundaries. So can you see a lot of white lines are there? Let me zoom it for you. Can you see the white lines? A lot of white lines are there. So when you rolled it, you can see a lot of grain refinement was there. And this heterogeneity is gone. The same thing which we have seen in the XRD. Either it's XZ surface or XY, there is no heterogeneity. Here the heterogeneity existed till the hot isostatic pressing process. So that's the edge received thing. That's the hot isostatic pressing thing. You can see the heterogeneity is there. The highest heterogeneity in the edge printed case. And here it's little lower. Here it's almost gone. Now, what this hot rolling or hot isostatic pressing is doing, we are applying pressure on the material. So you can see the grain size is coming down, and it's in case of hot rolling, it's coming down significantly, right? It's somewhere close to 60 to 30, let's say, or 50% reduction in the grain size. Now we have measured the hardness. Now one would claim, like, the standard thumb rule is, if the grain size is low, the hardness or the mechanical properties shall be pretty good. However, in this case, we are getting a very high hardness for the edge printed case. What can be the reason? Can you imagine in your mind without telling me? Can be the reason, like for the edge printed case, we are getting pretty high hardness. However, for the hot rolling, where the grain size is the lowest, shall be the highest, right? But it's not. The answer lies in these white lines, right? White lines means high amount of low angle grain boundaries, or technically high amount of dislocations are there. What these dislocations are doing, right? If you have applied any load, let's say you are measuring the hardness, you are applying a load and then measuring the hardness, right? When you are applying any load or anything, if a lot of defects were there or dislocations were there, this will hinder the movement of your atomic structure or the elements or the grains. It will stop the movement of your atoms, and that's how, if your atoms are not moving, that means it's high hardness, right? So it's playing the role. Let's say even having the highest grain size, it's overpassing the 50% of grain size reduction, right? And for this hot isostatic pressing, grain size was not that low, so that it can provide a pretty good high hardness, and the dislocations also gone away because you are heating it during applying the pressure, right? So your defects are not here, and the grain size is also moderate, so that's why it's showing you the lowest hardness. However, it cover up some amount of hardness because of the fine grain size, right? Now we calculated the wear volume, because you are as I said, these medium entropy alloys has a great application in space applications. So you need to calculate the wear and tear, how it's going to take place. Now, for the wear volume is directly proportional to the hardness. If any material is having a higher hardness, it shall have lower wear volume or the wear rate. The highest hardness was for the edge printed case. That's how it's showing the lowest wear volume. Similarly, the hardness was the lowest for hot isostatic processing process. Here, when the hardness was the lowest, wear volume is the highest. And when the hardness is in somewhere moderate range, it's approaching the highest one, but it's not the highest one. So your wear volume is this much. And to measure the wear volumes, we have used a nano inventor. I'll show you in next slides what we did. We use a nano inventor and mark a scratch. I believe many of you are working with the wear and all these things. So that's a pretty good practice to measure the volume. So area under the curve multiplied by the length, you can means area in this, the wear area, and then calculate it by marked, and the wear volumes have been calculated. Now, these SCM images are depicting a pretty good surface morphology, what's happening after the wear test. As you can see it, it's showing the highest hardness. You can see it kind of a brittle kind of fracture. High amount of defects were there, high amount of dislocations were there. So it's showing kind of a brittle behavior. While during the hot isostatic pressing case, you can see it very smooth scratch lines were there and very sharp featured slip bands were formed. That means these are the deformation features, right? When you are applying any load, you will see these are the stress relieving features. That means stress is trying to reduce down, and these kind of features will pop up, right? And in the case of hot rolling, here the wear volume has been on the moderate side because the grain size has been increased, and the increased grain size, it's providing strength because of the high number of grain boundaries that are registering the deformations. So now we are moving to the closure of it. I believe it's pretty late for you guys. So the last slide for the day. We have investigated the corrosion behavior of it for the complete replacement of the means. You can completely recommend any product only when you have all the calculated properties from the microstructural point of view, mechanical point of view, and corrosion point of view, right? For the edge printed case, we have the lowest corrosion resistance, and for the hot isostatic pressing, we have the highest. Earlier, it was like giving us pretty good mechanical properties, right? However, in terms of corrosion, it's reversing. Hot isostatic pressing is giving us pretty good corrosion resistance, or even the highest among all these three. So the justification for this edge printed, because it has the lowest one, it has a lot of defects. So when you are when your material is trying to passivate, the passive layer will break down at the defects point, and that's why your corrosion resistance is lower in case of edge printed case. In case of hot rolled, it is expected to be if someone is thinking like, okay, all the mechanical property and everything was good, then why the corrosion resistance is lower for the hot rolling case? The answer lies here. Can you see the grain size of it? It's very fine. From zooming it here. Can you see the grain size? Very fine grains are there. And if anyone is having basics of the corrosion, they knew it like if higher grain boundaries are there, those grain boundaries are acting as a defect, right? So in the high number of grain boundaries, high number of defects will be there, and subsequently a lower corrosion resistance, even though it's having better than the edge printed case and than the hot isostatic pressing, it's having the lowest number of defects and the moderate grain boundaries among all these three. So in that way, it's having the best corrosion resistance. So now it's up to you. Where is your application? So you have to trade off between either the hot rolling or hot isostatic pressing. Your material has been exposed to the corrosive environments, go with the HIP process. If your material is exposing through the tough mechanical conditions, then go with the hot rolling conditions. So based on all these results, here are few of the conclusions. So the conclusions have been combined for that 1, 2, 3, 4 minute heat treatment, that condition, and this cobalt chromium nickel analysis. So during the heat treatment, we have seen that the material was extremely sensitive with respect to the time. So that's why these biomedical implants are extremely costly, because you need a really controlled temperature, heating, everything, right? heating rate, cooling rate, then only you can make them available for the specified purpose. So at the 4-minute heat treatment condition, the R phase solver's temperature, the heating was around 850 degrees Celsius. The deformations or the dislocations were not there. You remember that at 4 degree, all the blue color was there, neither the green or all those white low angle grain boundaries also disappeared. If you remember that thing. So this conclusion says the same thing, that it was no longer observable. Time was insufficient for the microstructural changes. So, and for the precipitation dissolve as well. So we are claiming that whatever the transformation temperature changes or whatever we are getting, it's solely responsible for the dislocations only, right? Not because of the grain size or any precipitate, because we have not given sufficient time to do anything with the grain size or the precipitate. So it was solely responsible for the dislocations only. The next conclusion is there is no single study available till now that has been separated the role of grain size and dislocations, right? So our study is well appreciated in the academic community, and it has been published just few days, or let's say a month ago, not more than that. It's in 25, right? It got already 4 or 5 citations. So means the community is appreciating this work pretty well, because that's the one of its kind investigation. Now, coming to the conclusions of the medium entropy alloys, we have minimized this textural anisotropy if you are hot rolling it. That's what we showed in the EBST maps. The wear anisotropy also has been minimized. The difference between the wear volumes for X and Y, what I'm trying to say is, you can see it. That's the anisotropy in the wear volume with respect to the XZ and XY surface. Can you see it? It's pretty huge. And that has been almost eliminated in the case of hot rolling. So in that sense, we are saying the anisotropy has been eliminated in terms of wear volume. Similarly, the microstructures were also, the microstructural anisotropy was also eliminated. Now it's up to you what your application is. So either you can select hot rolling or hot isostatic pressing. These are the corrosion rates. So significant difference is there, but it's up to you where is your application. So I would recommend, before going to the commercial scale of additive manufacturing, it's up to you. Like, you have to first identify the appropriate additive manufacturing process, do a rigorous analysis, then only you can rationalize your applications. Otherwise, the criticism will always be there, like this additive manufacturing is having not that much of a scalability, right? So it might have in near future, but as of now, if I have to be true, it's not that much scalable. Let's say if someone is saying I'm making my product by casting, it will be pretty cheap, right? With the additive manufacturing, if you're putting cost, means higher cost in it, make your product really good. And particularly this biomedical implant segment, it have huge potential. Or second thing is, space applications also have a pretty huge potential for it. One more thing I'd like to share with all the audience, there is another specific application which we have not covered it here, because it's the sensitive information that cannot be shared. But people are using these additive manufacturing techniques for the repair of aircraft components. Instead of replacing the whole aircraft component, you can try to repair the same component and enhance the life of that component. In that way, additive manufacturing is gaining significance in this industrial scalability. That's all I would like to say. Thank you for your kind attention, everyone. That's all. You're free to ask any question, please. Shall I stop sharing? Yeah.
Any questions from your side, participants?
Shall I stop sharing the presentation, or anyone wants to?
Yes, sir. Yes, sir. Any query? I think
If you are, means, if you're not having queries or anything, I'm leaving my email address. If you wish to connect later, you can send me a message, and I'll try to respond at the earliest. I dropped my email, so all of you can connect with me. If you have any queries related to the synchrotron diffraction or any scalability issue, you can connect me anytime. Thank you.
Thank you, sir. Once again, I would like to thank you for this wonderful session.
Thank you.
Dear participants, thank you for your actively participation today. Thank you all. We will meet tomorrow. Then
Thank you, Dr. Gurpej.
Thank you,
Thank you.
everyone.
Thank you, everyone.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, Dr. Gurbej, once again for.
Thank you, sir. Thank you very, very much. Thank you.
Pretty well faculty development program. I hope everyone will get something from it. Thank you very much.
Thank you, sir. Thank you for joining us.
Thank you. Bye.